Okay, so this problem asks us to find the normalized vector that is orthogonal to each of these states. So our first one is phi 1. So to normalize this, we'll need to take the interproduct of phi 1 with an arbitrary vector. So right here is our arbitrary vector, and here is our phi 1. So you can see we just have constants, coefficients a and b. We need the arbitrary vector to be a bra and not a ket. So we will use the complex conjugate in the inner product. So go down and we see here's my inner product, and we are setting equal to 0. When we do a little bit of algebra, we see that when we do the inner product, the inner terms cancel. So that's why I have two zeros here. So we're left with 0 equals the complex conjugate of a times 1 over the square root of 3 plus b, or the complex conjugate of b times I times square root of 2 over the square root of 3. And we solve for a, and we are left with the complex conjugate of a is equal to negative I, or we're left with the complex conjugate of a is equal to negative the complex conjugate of b times I times square root of 2. So let's put a value to the complex conjugate of b. If we set equal to 1, that makes the complex conjugate of a negative I times square root of 2. And then to solve for regular a, we just flip the sign, so we get a equals I times square root of 2. So our our vector is phi a is equal to I times the square root of 2 for spin up plus 1 times spin down. To check for normalization, we do the modulus of a squared plus b squared, which are the coefficients we just found. And we find that equals 1, so it is normalized. For the second equation of state, we do the same thing to find an orthogonal vector. So we take the inner product of an arbitrary vector. I have coefficients, the complex conjugate of a2 and the complex conjugate of b2, and we go through the algebra again, and we get a2 is equal to 2b2. We set b equal to 1, so 2 is equal to a2. And to normalize, we take the inner product of the equation of state we just found, so that's phi b, and we take it with the inner product with itself, and we set that equal to 1, and we multiply it by some constant c. So after we take the inner product, we get c becomes a complex conjugate c times c, which ends up with, which simplifies to the modulus squared of c. So below here we have 1 times the modulus squared of c times 5. So then we solve for c, and we get the square root of 1 over 5 is equal to c. So our orthogonal vector is phi b is equal to 2 over the square root of 2 spin up plus 1 over the square root of 5 spin down. Now for the third equation of state, we do the same exact thing. We have another arbitrary vector we have our coefficients, the complex conjugate of a3 plus the complex conjugate of b3, and it's in an inner product with our equation of state for phi 3. And go down and we solve for the complex conjugate of A3, and we get complex conjugate of A3 is equal to complex conjugate of B3 times e to the I pi over 4. Again, we chose the complex conjugate of B3 to be 1, and we get the complex conjugate A3 is equal to e raised to the I pi over 4, which so then that infers that A3 is equal to negative EI pi over 4, because when we get rid of the complex conjugate, we just switch the signs. Plugging this in back into the arbitrary vector, we have phi c is equal to negative EI pi over 4 for the spin up plus our spin down. To normalize, we take the inner product with itself and set it equal to 1. So again, we go through the same steps that we did last time, and we are left with c is equal to 1 over the square root of e raised to the I pi over 2 plus 1. So this tells us, once we multiply this back through our vector, we are left with phi c is equal to this. I won't read it out because it's pretty long. Part B, we are asked to calculate a bunch of inner products for phi I and phi j. So the first one is this, phi 1 time, or taken with the inner product of phi 2. We get just the inner terms cancel, left with the outside terms. We get this. Same steps follow for phi 1, the inner product with phi 3. And then again for phi 2 and phi 3, and then phi 1 and phi 1. And phi 2 and phi 2, and phi 3 and phi 3. So this is my solution to problem 1.2 in our text.